Right, on this section of our second video, still under reflection, we are going to look at images formed with plane mirror. Images formed with plane mirror. Images formed with plane mirror. Now, let's see what is our objective here. The main objective here is that you are expected to be able to draw ray diagram and locate position of the image produced by an object placed at a specified distance from a plane mirror. Right, this is the objective. Draw a ray diagram and locate the position of the image produced by an object placed at a specified distance from a plane mirror. Now, and state the characteristics of the image. Two things. You must be able to draw a ray diagram to locate the image position for an object which is at a specified distance from the mirror. Then you must also characterize the image. Now, I'm going to start by a diagram. We go straight to what we are discussing. Let's suppose we have a mirror here. I'm locating it vertically. Now let's suppose this is going to be my horizontal. Let's suppose that I have an object at this position. I'm going to put it as a dot, my object. And this is the back of the mirror. And this is the reflective surface, and this is the back part of the mirror. Now, this object, now a light ray can strike the mirror at that point of incidence here. Now, and then it's reflected in this direction. Now, the reflection is in such a way that, check, it must always fulfill the angle, the law of reflection. Always. If this is my normal, then this is my angle of reflection. This is my angle of incidence. Now, if I were to put an eye at this position, I put an eye there, here. This is an observer who is observing this object. This ray comes from, this is the object, and it strikes the mirror, and it's it gets into the eye of the observer. Now, according to the observer, he doesn't see this light coming from this object, but he sees it coming from a straight line somewhere behind the mirror. He doesn't see it coming from here, but from somewhere behind the mirror in a straight line. Now, if a ray goes and strikes the mirror perpendicularly, it is reflected backwards along the same path. But if we project backwards, then where the two projected rays meet, this is a projected ray, this is a projected ray, we are extending them behind the mirror. Where they meet, this is where we have our image being formed. Now you'll find that this, let's call it D naught, that is object distance from the mirror. And this one, we can call it DI, image distance from the mirror. So in this manner, you find that DI is equals to D naught in magnitude, of course. Right. So what the eye, the observer, sees is an image at this point behind the mirror, an image behind the mirror at this point, and it will be at the same distance from the mirror as the object is in front of the mirror. So this is the ray tracing of an object image in a plane mirror. This is our plane mirror. This is our plane mirror. This is the ray tracing that happens in a plane mirror. And so that we can locate our image here from an object placed at a specific distance from the mirror itself. So we locate the image using the extended rays. These are the extended rays behind the mirror. Where the extended rays converge, then we have the location of our image at that point. Now, this can happen. This you can do with any object. You can do this with any object. For example, let's suppose I have a mirror here. Now, let's suppose you can have a person here who is watching himself in a mirror like that. And the person is standing like that in the mirror. Now, you may find that if he is observing himself, now then a ray from the top of his head will come to the mirror, reflects back into his eyes, like that. Reflects back into his eyes. Now, a ray from his foot can strike the mirror and reflects into his eyes again like that. Right. So similarly, this guy, when he sees himself in the mirror, this ray, which is reflected, he sees it as coming from somewhere down here. And if you were to make another ray that strikes the mirror directly somewhere here and there, then you find that if you extend, then you will see here his foot. You will see his foot somewhere here. And similarly in the head again, you find that when he sees this one, he sees it as coming from somewhere there. But when you use the normal ray that goes and strikes there, and then you extend backwards, they will meet somewhere here. And so this whole region is going to be the gentleman again, like that. So he sees himself in that manner. So you can actually do ray tracing on any object and get its position for an object at a specified distance from the mirror. Right. So these are just examples of how a plane mirror forms up an image. Okay, so in brief, let's look at the properties of the image formed with a plane mirror. Properties of the image formed with a plane mirror. Now, we say that one image is as far behind the mirror as the object is in front. Now, second point is that image and object are of the same size. Magnification is 1. Image is laterally inverted. Right, so these are the characteristics which are found in the image formed with a plane mirror. Right, when you are doing ray tracing of these diagrams, you will observe it on your own. Right, now let's look at the next point of discussion, which is image formed with spherical mirror. Spherical mirrors. Right, we saw the image formed by a plane mirror. Now we are going to briefly look at images formed with spherical mirrors. Right, our objective, let's call it objective 4, says you are expected to distinguish between convex and concave mirror. This is our objective. You must distinguish what is a convex mirror, what is a concave mirror. The two of them, distinguish between them. What this implies is that we are talking about types of mirrors here in terms of curved mirrors. That is, we are talking of types of curved mirrors, and the types of curved mirrors we have are concave and convex. We have two types, concave and convex. Of course, there are others which we are saying parabolic and so forth, but we are not interested in studying them at this stage, this is not the scope of our interest. Right. So let's look at these mirrors one by one. Now, one important aspect here is how light behaves when it strikes these mirrors. So let's look at the concave mirror. The concave mirror. Now, it has a caved surface. It has a caved surface, which is actually part of part of, let's say, the circumference. The circumference of a sphere. Right. So it's a section of the sphere. Actually, we are taking a section of a sphere and making it a concave mirror. We are making a mirror out of a section of a sphere. Now, okay. Now, a key property which is approximately satisfied by spherical mirrors is the ability to focus a beam of light parallel to the optical axis. This is one key property which is made use of in designing spherical mirrors. Right. Remember optical axis, we studied it when we were looking at lenses, and it's a line that passes through the center of the lens, we said, and maintains symmetry of the lens. Right. The same applies to a mirror. Now, diagrammatically, we can say the concave, we can represent it by this curved section, and this side is where the metal coating is. Metal coating on this side, and this side is the reflective side. Now, rays come in parallel to strike this side of the mirror. So these are incident light rays in this direction. Now, at the center here, sometimes it's called the vertex, sometimes it's called the optical center. This line is still the principal axis. Now, it has this point which we call the focal point, and another point which we call center of curvature. So this is principal axis or optical axis. Optical axis. So check. It has a focal point. It has a center of curvature. Now remember we said this forms a section of a sphere that would go around. So this section, if it were a sphere going around completely, then this would be the center of the sphere. The center of sphere. So we call it center of curvature. Center of curvature. That is center of the sphere. If we were to make a complete sphere of this section, then this would be its center. So the distance from C to optical center, let's call it V for vertex. The distance from C to V, in other words, CV, is the radius of curvature. The radius of curvature. And FV is focal length. Focal length. The same concept as we studied in lenses. Focal length of this concave lens. Right. Now check. We say for this concave lens, for this concave mirror, the edges always bend toward oncoming light. Always bend toward oncoming light. That is, this is how it bends. The light is coming this way, and it bends. These are the edges. And these edges, they bend towards the incoming light. This is incoming light. So this is a concave mirror. A concave mirror. Right. And check. The reflective surface is also towards the incoming light. And the non-reflective surface is away from the incoming light. Okay. Right. We can also say the reflecting surface, check, is on the inner surface. It's on the inner surface of the sphere. Remember, we make the whole surface. If we were making the inside of the sphere, the reflecting surface. So it's in the inner surface of the sphere. Right. Check. And we say the mirror surface caves away. It caves away from the viewer. Or incoming light. It caves away, goes away. The cave goes away from the incoming light. Right. Now, so if we can look at it again, F, the focal point, and C, the center of curvature. They are both located toward the incoming light. They are both located toward the incoming light. In other words, this side you find the focal point, this side you find the focal point, and this side you find the center of curvature. Both of these are located toward the incoming light. Right. So this is one way of identifying a concave a concave mirror. Now let's look at the convex mirror. The convex mirror. Convex mirror. Right. We can represent it diagrammatically again in this manner. Now check. It is still the section of a sphere, but this time the inner surface is non-reflective, and the outer surface here, this is the reflective surface, and this one is non-reflective surface. See? Right. So light approaches in the same manner, like that. And at the center here, we still have our optical axis or principal axis, the same. And here we still have our vertex at here, or optical center. But now the focal point is now behind here, and the center of curvature is here at the back. And the mirror receives light on this side. Right. So we can say then that the edges of the mirror, the edges of this mirror always bend away from the incoming light. They always bend away from the incoming light. Right. The reflection takes place on the outer surface. Reflection takes place on the outer surface. On the outer surface. Now, the center of mirror surface bulges out toward the incoming light. The incoming light. Right. It bulges towards the incoming light. You can see the center here of the lens, the mirror bulges towards the incoming light. Now, and at the same time, you can see also that F and C are located away from the incoming light. From the incoming light. Right. So this is the convex mirror. This is the convex mirror, and these are the characteristics of it. Okay, now let's look at how the law of reflection, how the law of reflection is valid. How the law of reflection is valid. Now, if we draw, let's talk in this case, we have a convex mirror. Now, and let's suppose this is my optical axis. Now, and let's suppose that this is the center of curvature. Now, you will find that if I were to draw a straight line to the surface from the center of curvature, remember this becomes the radius of curvature. It's a radius of the sphere. Now, wherever it touches here, the circumference, it makes an angle of 90 degrees. So if I were to draw a tangent at that point, then this same line becomes my normal. So if I have a ray that comes and strikes this point, which is point of incidence, and this ray is parallel to the principal axis, it's going to be reflected in that direction, such that the angle of incidence is equal to angle of reflection. Right, at this point, we can call it P. Right, so we have to draw a tangent here, and that tangent, then we draw a normal to that tangent, and then we can draw our incident ray and a reflected ray. And the two angles must be equal. Like that. Right. So the law of reflection must be obeyed at the surface here whenever light strikes this surface. The law must be complied with. Right. So we say then that reflection occurs at surface. Reflection occurs at surface. Right. The law of reflection, still holds at each point of the curved surface. Right. You can always draw a surface tangent and erect a normal at that point on the surface where the light is incident, as we have just shown in the diagram. You can always do that. This you can also do with the concave. Remember, this is convex, but you can also do it with the concave. This is convex mirror, which we have used to demonstrate this, but you can also do it with the concave mirror. Right. Now, Let's look now at the next aspect, which is behavior. Behavior of light rays when they strike a mirror. Behavior of light rays when they strike a mirror. Right. Let's look at that. How do light rays behave when they strike a mirror? Our objective, let's call it objective number 5. Now, our objective is to draw rays parallel to the principal axis and locate the position. Locate the position of the principal focal point of each type of spherical mirror. Right. In other words, here we are trying to analyze the behavior of light rays when they strike a mirror. Now, our intention is we must locate the position of the principal focal point. In other words, we need to identify the focal point of the mirror using rays that are incident on the mirror, and these rays are parallel rays which are incident on the mirror. So we must be able to use the parallel rays incident on the mirror to identify the focal point of the spherical mirror. This is the whole point, and this is for both convex and concave mirror. Right. Now, so as we look at that, we first define what we mean by parallel rays. What do we mean by parallel rays? These are light rays. These are light rays from a distant object. From a distant object. E.g., we can talk of the sun, etc. Right. Now, the law of reflection is applied at each point, on the surface of the mirror. Right. On the surface of the mirror, where the rays are incident, we apply the law of reflection on the surface where the rays are incident. Now, the rays are reflected. So as to pass through the focal point. F in front of the mirror. Right, here we are talking of a concave mirror. Right. The rays also may be reflected in such a way that they appear to come from a point behind the mirror. Right. In this case, this is in case of a convex mirror. The point is the focal point. Right. So let's look at what happens. Let's start with concave mirror. Let's start with concave mirror. Now, in terms of concave mirror, let's shift this. Right. So diagrammatically, let's suppose I have a concave mirror like this. And remember we said this is the non-reflective side. And then here I have my optical axis or principal axis. Right. This is my optical axis. Now, what we were saying is that when light rays come, they strike the mirror like that. They come, but they are parallel to each other or parallel to the optical axis like that. They are parallel. Now, all of them, when they reflect, they do so in such a way that they have to pass through the focal point. This one reflects but passes through the focal point. And this one reflects and passes through the focal point. Like that. Right. The same applies down here. If you have a ray parallel to the principal axis, it is also reflected passing through the focal point. And the same applies to this one. It's reflected passing through the focal point like that. And this is our vertex, which is the optical center. And this is in case of the concave mirror. Right. So this is our focal point, and the focal point is where incident parallel rays come to focus. Incident parallel rays come to focus at the focal point. Right. So this is what happens in terms of a concave mirror. Now, suppose we have a convex mirror. Let's suppose if we have in this case a convex mirror, what happens? Now, if we have parallel rays, the parallel rays come like that. They come, and the parallel rays, let's put also on this side. All parallel rays, they come. Now, you find that they are reflected in such a way that this is the focal point. So when they reflect, they appear to come from the focal point. This one, when it is reflected, appears to come from this point. And this one, when it reflects, it appears to come from there. The same applies with each one of these, each one of them, each one of these ones, like that. They all appear to be coming from this point. This is in terms of the convex mirror. The convex mirror. So this is the focal point. In other words, it's a virtual focal point because no rays really arrive at that point. While in the concave mirror, it's not a virtual focal point, it's a real focal point because real rays or rays of light or light actually passes through that point. Now, this is our vertex, this is our principal axis. Right. So basically, in terms of how light behaves when it strikes a concave and a convex mirror, this is what happens. Right. Okay. Now, we are going to look in the next part of our video about ray tracing. For now, on this part of the video, we have just identified the mirrors which we are going to discuss in terms of image formation. So we meet in the next video about ray tracing.